Hello and welcome back. Let's continue looking at logarithms, and we'll start by finding the domain of a logarithm function. And what we have to remember is that we can only plug positive numbers into a logarithm, as in the domain of a logarithm of the basic logarithm function here is going to be the numbers from 0 to infinity. So this is a lot like a square root function, where we can't take the square root of a negative number. But unlike a square root function, this is different because we can't even take the log of 0. You're not allowed to take a log of 0. You are allowed to take the square root of 0. So just to reaffirm, the square root of 0 is 0, so this exists. The log base b of 0 does not exist. So you cannot take the log of 0. So when we want to find the domain of a logarithm function, what we can do is we can look inside of our logarithm and we can see, this right here, this x minus 5, this has to be a positive number because I can't plug a negative number, nor can I plug 0 into a logarithm. So when I look at this, we see that x minus 5 has to be a positive number. Well, if I add 5 to both sides, we get that x has to be greater than 5, and I can write this as an interval. So the domain of this function is going to be all of the numbers that are bigger than 5. So 5 to infinity. And by looking at this, we can kind of see this in essentially one step. What x's could we plug in here to make this positive? Well, anything bigger than 5 would work. Anything less than 5 wouldn't, and neither would 5. So we have a round parenthesis here, not a square bracket. So the domain of the function, we just want what's inside of the log to be greater than and strictly greater than 0. So there are a couple of common types of logarithms. The first one is just called the common logarithm, and this is the logarithm base 10. Whenever you see a logarithm without a base written, so this is f of x is equal to log x, and we don't see the base there, the base is 10. So don't freak out if you don't see a base there. If no base is written, it means base 10. So log base 10 of x is the same thing as just log of x. So this is just a shorthand because log base 10 comes up often enough that if you don't write the base there, people will assume that it's log base 10. So let's do a calculation with this. So the percentage of the adult height of a boy who's x years old can be modeled by this function here. So this is a little bit complicated. We'll come back to that in a second. So it's essentially asking what percent of his adult height has a boy attained at age 10. So when they're at age 10, are they half of the height of what they'll be when they grow up? Will they be 3/4 of the height, one fifth of the height? This is what this equation is modeling. This is going to be 29 plus 48.8 times the common logarithm, log base 10, because we don't see a base there, of x plus 1. So at age 10, we just want to plug 10 in for x. X is just how old the boy is. So this is going to be f of 10 is 29 plus 48.8 times log base 10, but we don't have to write it, of 10 plus 1. So again, we're plugging this into our function, and we've got some parentheses around this, so we want to resolve that first, order of operations. So this is going to be log of 11. And this is something that we can plug into a calculator. You can even type this into Google. And what you get when you do this, it'd be good to check. We get something that's about, so after we round, it's 79.8. So if you were to type this into Google, you would write almost exactly this. You would write 29 plus 48.8 times, which is the star, and you would just type out log parenthesis 11. Most scientific calculators and graphing calculators will have a log button as well, and there will normally be 3 types of log buttons. There will be a basic log button without a base there. I shouldn't call it a basic log function. There will be a common log function without a base, which we assume is base 10. There will often be a log base b of x, and you just have to press the buttons in the right order to give it the base and then what you're plugging in. And then there's a third type of logarithm, which we'll see at the end of this video. So for the moment, let's look at some properties of common logarithms again. So, and I've written the original property over here, and we'll just write it in terms of the common log as well. So whenever we have the log base b of 1, this is asking b raised to what power is 1? Well, anything to the 0 power is 1. So log base 10 of 1 is also 0. Log base b of b is always 1, because b to the first power is b. So this is also just going to be 1. And then exponentials and logarithms are inverses of one another, so they're going to cancel out. So log of 10 to the x power is x, and 10 to the log of x power is also going to be x. Again, they're inverses of one another, so they'll just cancel out. So let's do another question here. This is actually interesting, and it sort of describes something that we've seen before with the Richter scale. So the Richter scale, the intensity of an earthquake, we can plug it into this equation, and we can figure out the magnitude of the earthquake. So say if there's a magnitude 8 earthquake, this is very highly destructive, something that will collapse buildings. Whereas if it's a magnitude 4 earthquake, there will be some shaking, but normally not a lot of damage. So this is how we find the magnitude of an earthquake. The magnitude is r, and the intensity would be measured by scientific instruments. And we're just going to take the log of I, the intensity, divided by I naught, I sub 0. And I sub 0 is just the intensity of what the textbook calls a barely felt earthquake, meaning not much of an earthquake at all. Scientific instruments will not even be able to pick it up. So this is just the very, very weak earthquake. So the question is, what is the magnitude of an earthquake that's 10,000 times more intense than this weakest earthquake? So to start with, if I naught was the intensity of the very weak earthquake, of the barely felt earthquake, one that's 10,000 times more powerful is going to be 10,000 times I naught. This is going to be the intensity of the bigger earthquake. So let's plug this into our formula and figure out what the magnitude would be. So R is just going to be the common log of the intensity of the big earthquake. So this is going to be 10,000 times I naught divided by I naught. So right away we can see that we'll cancel out some I naughts. So we're going to have the log of 10,000. So after we cancel out I naughts. So here I need to know what the log of 10,000 is. And what I'm going to do is I'm going to use the properties of logs that we've already had. 10,000 is the same thing as 10 times itself 4 times. So essentially, this is kind of like scientific notation here. So this is log of 10 to the 4th power, but everything cancels out, and we're just going to get 4. This is a log base 10, and this is an exponential of 10 to the 4th power. Logs and exponentials cancel to give 4. So to put this in perspective, if we have a magnitude 0 earthquake that we can barely feel, one that's 10,000 times more powerful only has a magnitude 4 earthquake. One that's 1,000,000 times powerful, if you plug everything in, is going to be a magnitude 6 earthquake. So it's still not even getting up to the magnitude 8 earthquakes, which are magnitude 8 to 9 earthquakes, which are unbelievably powerful. So we've looked at common logarithms. The last one are natural logarithms, natural logs. And this, instead of having base 10, this is base e. So e is the number that we saw last time that shows up with exponential functions. So when you want to write log base e of x, we're normally going to write ln x. And this is how you read this, ln x, which is just the natural log of x. So let's work with the natural log for a little bit. So the first question is just to find the domain of these functions here. A logarithm is a logarithm. It doesn't matter what base it is, and we can only plug in positive numbers into our logarithm. So for instance, the domain of this function, we can only plug positive numbers into here. So 4 minus x needs to be positive. If I subtract 4 from both, let's not do that. Let's add x to both sides. So we can see that 4 has to be bigger than x. Or instead of saying 4 is bigger than x, x is less than 4. It's the same thing. I've just written it in a different way. So the domain of this function is going to be all the numbers that are less than 4. So from negative infinity up to 4. Again, I can't plug in 0, so I don't want to include 4. I can't include that endpoint. Here I have the natural log of x squared. So again, I need what I'm plugging into my logarithm, just so happens to be a natural logarithm. I need this to be greater than 0. Now, if we think about this for a second, when is the number squared going to be greater than 0? Well, if I put a positive number in here, a positive number squared is positive. But also, if I put a negative number in here, a negative number times a negative number is also positive. The only thing I can't plug in here is 0, because 0 times 0 is 0. So from this, we can plug in all positives, all positive numbers. We can plug in all negative numbers, but we can't plug in 0. So the domain of this function is going to be all the numbers from negative infinity up to 0, so all the negative numbers, all the positive numbers, and we'll stick them together with a union. So there you go. There's a natural, couple of examples of natural log, and we'll finish up very quickly with some properties of the natural log. So again, the log base b of 1 is always 0. It doesn't matter what the base is. So the natural log of 1 is going to be 0. And I apologize, my L's look like my 1's here. Sometimes you can write it as ln of 1 with a script L, just to make sure that your L's and 1's look different. But I hope that this is clear enough. Log base b of b is always 1 because b to the first power is itself. So log base e of e is also 1. Natural log of e is 1. And then the last couple are just the fact that b is going to be the natural log is going to be the inverse of the exponential with a base e. So natural log of e to the x is x, and e to the natural log of x is also x. And I will stop there.